Okay, let us see how we handle this question when we have forces producing simple harmonic. It's a bit different, but let us handle it. It's also very easy, don't worry. A body of mass 500 grams is attached, so it's attached to end B of a light elastic string AB of natural length 50 centimeters. The system rests in equilibrium with the string vertical end A fixed. The body is then pulled vertically downwards through a small displacement and released full stop. If the motion after is simple harmonic of period pi over 5 seconds, find the modulus of the string. So start by summarizing. In our summary, they are giving us mass 500 grams, which will be the same as 0.5 kilograms. They're also giving us the length, the natural length of the string as repeated centimeters, which is the same as 0.5 meters. So we have converted only once. So now we draw a simple sketch of the first sketch before it was pulled. For the first case, this is what we have. This is our string. We have our particle. This is the particle mass, 0.95 kilograms. Of course, we're going to exact weight, 0.5 times V. We are going to be having tension in this string, of course. It's going to act in that order. So, this is our A. And then we know that from there up somewhere, we are going to be having the length of the natural length. Then from here up there, we are going to be having the extension, because after stretching the string, we are causing an extension there. So which I am calling E. So it means that now, from there, now they are telling us that the particle is still rests in equilibrium. So in equilibrium, it means that now, if I resolve vertically upwards like this, of course I'm going to be having T equaling to these forces are going to be balancing, equaling 0.5 G. Okay, but now I move from hook law. I know from Hooke's law, know that our T is equaling to lambda E over N. So putting it there, now I have 0.5 E. Now I have this as lambda E over N equaling 0.5 E. I call this equation 1 with the H. Now I come to the second case. Body is then pulled vertically. So now this is the case we am now going to also draw a sketch for it. Now it's pulled vertically through a displacement. Okay, I'm saying let X be the displacement when it's pulled. Now, still it's going to be, its end is going to be there, then it's going to be pulled in that order. We are going to have our particle there, 0.5, then this is going to be our mass, 0.5 B. Now, when this particle is pulled further, it means that the tension in the spring is going to change. So meaning, the tension in the spring now is going to change. So let us call it T, now 1. Because after giving it a further pull, it's going to change. The tension is not going to remain the same. As I can show you here. If the spring is like this and I pull it here, up here, and then I pull it further, it means that the tension before is no longer the same. So now, it means that now we have from there, we have our natural length up to somewhere there. Now, we are going to be having now the extension we had, this one, the extension we had E, then X, okay, I'm going to have the extension I had before, that is E, then another extension I'm giving it as X, I'm giving to that particle. It implies that the wall from here up here, the extension is going to be now x plus e. That's the new thing I'm having. So now, from there, what happens? What is going to happen? Now, this is the other displacement I'm giving now from here. This is the other displacement I'm making after putting it vertically downwards. So, if I resolve going downwards in that case, we always know, using Newton's second law of motion, I resultant force is equal to the mass times acceleration. Now, after giving it this and then there is the motion is producing, they're telling us now is going to be simple harmonic. So meaning our acceleration is going to be the displacement differentiated into 2 times. So resolving this direction, we have now 0.5 minus 5d, then minus our one equal to the mass 0.5, then times our acceleration, which is going to be x now, like the acceleration produced by this displacement we are making. Now, it means that now here, our t, remember our t prime now is going to be given by lambda. The modulus in the spring doesn't change. What is always changing is the extension, which we have now as x plus e. Even the natural length of the string, in the assumptions we made, it does not change. So now, this is now, I think we see what the change, the difference here is this displacement we have added after stretching it further. From here, we stretch it further, that distance x there. So now, you know that from this one is always equal to t, which we have there. Okay, and then this one, we know it's going to be this. So this is going to be now lambda e from here, lambda e over L minus our t1, which is now lambda into x, then plus e, the whole over L, equaling to 0.5 x prime. So when we expand our brackets there, we have lambda e over L minus lambda x over L minus lambda e over L equaling 0.5 x down plane. This is the acceleration caused because of the particles moving in the simple motion, in simple harmonic after releasing it. So I think we see this one is going to cancel. We shall be remaining with negative lambda x over L equaling 0.5 x double prime. If I divide it this side, it's that my x double prime is going to be now negative lambda over 0.5 L into x. And I think now if we compare with what? With x the genome equaling to negative omega squared x. And if we compare with this, it implies that now our omega squared is going to be negative. It means that the whole of this is equaling to that. So lambda over 0.5 L. We have this, the natural length. Our natural length is here, 0.5. We need this. So it's that our lambda there. Or if I get because this one I can able to get from. So you see that our L there, so my lambda, but our L is 0.5 meters, which I substitute there. We are having this as lambda over 0.5 times 0.5. So my lambda here is going to be the square root of omega. It's going to be 0.5 squared, which is 0.25. Now I have two unknowns. Now I come back and I call that they gave me the period. So they told me that my period is equal to t over 5. The period from here. So my t here was pi over 5 seconds. Now I know what period is. Because I know that period is always equal to what? To 2 pi over omega. So if I want to get omega here, I'll get it as, so this is pi over 5 equaling to 2 pi over omega. So it's that this is going to cancel with this. So my omega is going to be 10 rad per second. So if I have it, now I can simply come and substitute it there. So now from here is that now this is the same as omega squared equaling lambda over 0.25. So let me call this 2. From 2, you can able to see that we had lambda over 0.25 equal to omega squared. Our lambda is going to be 0.25 times, now this is which is 10 squared. And you can start now our lambda is going to be 25 newtons. So that's the modulus of elasticity they wanted us to calculate. So that's it. And then as simple as that, the number is done. There is gentlemen, I wish you